transcription. Yeah, awesome. Yeah, so in this module, we will be covering discrete one-dimensional metamaterials. So uh, let's say you can call them phononic crystals or 1D metamaterials, right? So there'll be a unit cell, and then that will be connected to the next unit cell and the next unit cell. So we'll consider a chain like this. So the question is, why 1D? See, 1D is the simplest system that we can analyze where there is periodicity. Of course, if you go to higher dimensions, you'll have 2D or 3D, but uh, it's it's not like the only reason why 1D uh, phononic crystals are being analyzed for is that they are simple. There will be a lot of practical cases as well where 1D systems truly represent uh, realistic systems. Let's say beams or rods, certain slender structures like that, or maybe certain axial torsion problems. But nonetheless, it is simplest, and that is the reason why we will start with 1D. So so if this is unit cell I, and then the next unit cell is maybe I plus 1, and the previous unit cell is I minus 1. So whatever structure we'll have, let's say whatever lattice configuration we'll have inside I, you'll see the same pattern repeating at I plus 1 and I minus 1 and so on. And there will be some sort of coupling. There will be some sort of coupling that will also repeat. Right. So how do we form the periodic coupling? Like how do we understand it? Let's take a simple example. Let's take a monomer. So what is a monomer? Monomer. What is mono? Means one, right? So we'll have other systems where, let's say, this is these are identical masses connected with identical springs. Let's say the masses are M, 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 all of them, and the stiffnesses are K, 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 right? And the particle motions, they are restricted, let's say, in the horizontal direction. If the particle motion is, let's say, if this is your x-axis and if this is your y-axis, it's also possible that you have a chain, one-dimensional chain that is periodic in x, but the particles maybe move in both x and y. So if the particles can move in both x and y, then it it may be a 1D chain, but it's not a 1D phononic crystal. So that is essential to understand. The one dimension here is also referring to the degrees of freedom inside a unit cell. So what would be the unit cell here? So it's very simple. Udbhav, do you have any questions? Yeah, so this is the unit cell. Yeah. Hi, Samanvay.
नहीं आएगी 2 टाइम सब। Hello, Shrikant sir.
Uh, Hey, Samanya sir. So, uh, today's module, I am discussing discrete 1D phononic crystals in metamaterials. So,
Okay.
so, yeah, so there are some certain things that you specifically want me to cover, so I'll ensure that those are covered at appropriate places. So you can let me know. So far, I've just started it. So far, I think what I've tried to explain is what is 1D phononic crystal. So so here we have, let's say, unit cells, right? So so this is the ith unit cell, and then to the right of it is I plus one, and to the left of it is I minus one. So you can have a chain, but it's not the chain that makes it 1D. Inside the unit cell, you need to have 1 degree of freedom. Let's say here we have x axis and y axis. So if the particle can move in x and y, then inside the unit cell you'll have 2 degrees of freedom. So 2 degrees of freedom will make it a 2D. Although it's a chain, it will be a 2D chain. So so we begin with 1D phononic crystal where it's a chain and each unit cell will have one 1 degree of freedom. So that's what we've just started. Uh, so yeah, like please let me know if there's anything specific. I know that you also work in metamaterials. So so broadly, we'll be covering 1D monomer systems, the block Floquet, um, how do we write how do we connect adjacent unit cells using block Floquet? Why do we take the same omega? Why do we take the same Q for adjacent unit cells? Um, then what are the degrees of freedom? What are the various bands? How are they linked? Then band gaps, then attenuation, and what is the relevance of complex values of wave numbers. I'm just letting you know broad list of things that will be covered. Then what is the relevance of complex frequencies? Then then the complex part of the wave number, we have something called continuity uh, of alpha, where alpha is the real part of wave number. So we'll be covering that, and we'll show that pass bands have a certain periodicity, but the attenuation bands or the band gaps, they don't have a periodicity. Then we'll show maybe one or two papers, introductory papers regarding it. Then we'll move to dimer systems. Uh, we'll discuss what is optical, what is acoustic band. We'll discuss band touching. We'll discuss band folding. We'll have a look at what the modes look like. Then we'll go to locally resonant systems. We'll see how the modes couple between the main chain and the local resonance. And then how does that produce a band gap? How is the attenuation in locally resonant systems? And then we'll also see that locally resonant systems, the attenuation profiles, they're unique when compared to Bragg. So what is that? Then yeah, how was locally resonant system idea? How did it come about? Then we'll see in phase and out of phase motions. Um, and certain papers, and then we'll see what happens the if you increase the resonance frequency of the local resonator. If you keep increasing it, then what happens as you keep increasing it? So that's an interesting case. Then we'll cover grounding. How does grounding? What is grounding? Uh, why do certain systems need to be considered like as grounded systems? Then what happens to grounded monomer? Then what happens to grounded in local resonance? Then we'll go to something that is called lateral local resonance. And by the end of this module, we'll cover something new that is called inertially amplified system. So this is the broad overview of what this module will cover. So do you have anything to say about that? Are you looking forward to anything specific? Yeah, okay. So you can let me know if you're looking forward to anything specific. So yeah, so this is a unit cell, right? Um, and we've said that the motion is constrained in x-axis. So let's say there is another particle here. There's another particle here. This is m. This is n. Right. So let's say this degree of freedom is u of I. Then this degree of freedom is u of I plus 1. This degree of freedom is u of I minus 1. So let's say what is the, if we have to write the force balance equation, we have to write it in the form of uh, let's say uh, net force in x on the body should be equal to mass of the body into acceleration, that is u of I double dot. So we'll write this equation. So what is f of x? Now essentially you'll see that when will this mass be pulled in this way? When the spring on the right is elongated. So when does the spring elongate? When, let's say, uh, u I plus 1 is positive and is greater than ui. So basically it's this is the net elongation of spring to the right. So this is being pulled in that direction. And then similarly you can write uh, force towards the left will be u of I minus 1 minus u of I, right? Yeah, it will be minus. So we can take, I think, positive notation will be easier. So let's just take for consistency, even this force is, let's say, this side, right? Then this is u of I minus u of I minus 1. These are the two forces. Then if you write the total equation, you will see it's right. So we get it in this form, and we can maybe simplify this by taking k common. So if you take k common, we get something like k add this plus this. I think Yeah, so what we did here, as you can see, is that we wrote the equation, the free body diagram for the particle in the unit cell, which is a monomer, so single particle. So we have a single um, equation. This is net force is equal to mass into acceleration. Right, and this consists of terms such as u of I, the displacement of the unit cell, and then these are the adjacent unit cells. And then we say for a harmonic solution, we assume u to be of the form u naught, and into, let's say, e power I times qx minus omega t plus phi. So this entire this is, let's say, the phase where your q is wave number, omega is your angular frequency actually. Right, and this is the extra phase term. So if you assume ui to be of this format and u naught like this is the amplitude, then then what happens is, if we find out what is the uh, double derivative, like time derivative of ui, you simply differentiate ui with time twice, and then this omega minus omega comes out twice, and then that becomes omega square. So essentially, this is characteristic of harmonics. Then further, now this is within the unit cell, right? This is within the unit cell. Now, how do we connect adjacent unit cells? Because the harmonic waves are traveling across the chain. So so how do you connect is using what we call as block-Floquet periodic boundary condition. Now, what does that say? That says that uh, so so if you have a linear system, if one unit cell is vibrating with a frequency, let's say omega, then because this is a linear system, even the adjacent unit cells and the entire chain will vibrate with omega. So this is characteristic of linear systems. So from there we know that u of I plus 1 will also have a frequency omega. And further, uh, how do we connect adjacent unit cells is, if there is some wave propagating, then that wave will have some wavelength, and if there is a wavelength, there is an associated wave number. So your block-Floquet periodic boundary condition connects adjacent unit cells using a specific wave number. So whatever Q that we used here, that yeah, whatever Q that we used here, that Q will be common for the adjacent unit cells as well. So, but but the value of x that we have written here, that x will be different. So x of let's say x of I is, let's say, x naught, then x of I plus 1 will be x naught plus a, something like this. X naught is the initial position of the 0th unit cell, then plus a is where a is the lattice constant, that's the distance between adjacent unit cells. So that's how you describe the position of adjacent unit cell. And similarly, x of I minus 1 is equal to x naught minus a. Right, so this is important. So if you substitute that, like based on that, what we get is the difference between ui and ui plus 1 is that ui plus 1 is ui times e power um, I to the power e to the power I q of a, whereas u of I minus 1 is ui times e to the power minus I q a. How did we get this? Like here in the formula, instead of, let's say, this x naught, instead of x naught, just substitute x naught plus a or x naught minus a. If you substitute that, you'll get this. So this is how block periodic boundary condition essentially connects adjacent unit cells. So what is the advantage of this? Let's say if you are analyzing a crystal, like a crystal is an infinite, never-ending pattern. So there would be in total infinite degrees of freedom, but we cannot analyze for infinite degrees of freedom in, like, conventionally. Then how do we do it? Is we see that the unit cells are connected. They are not totally independent degrees of freedom when we are talking about wave motion, uh, especially stable harmonics. So they're connected in some way, and that connection is the wave number. So through wave number, we are essentially able to predict, if we know the motion of one unit cell, we know the motion of any other unit cell if we know the distance between them, if we know the wave number. So that's how the block blockade periodic boundary condition helps uh, reduce infinite degrees of freedom uh, by making by taking use of the wave number, and then essentially brings it into one degree of freedom. So if you have a unit cell inside which there is 1 degree of freedom, you can analyze the crystal as a 1 degree of freedom photonic crystal. So that is the beauty of this periodic boundary condition. Now, so if we substitute these back into equation 1 here, then what we get, what we observe is that, so we get the equation something like this, and then if we further, if we use using Euler's formula, like uh, so the formula is for e power I theta is equal to cos theta plus I sin theta. Right, so we use this formula to expand this, and then we get this form, and then we do that, and then finally we get this is the equation of motion. So further, we can write cos. We can write cos of qa as 1 minus 2 sine square qa by 2. So we simplify this. Finally, we get something of this form. Then now we know that if we want to find the value of omega from omega square, um, while taking square root, typically you would say it to be plus minus omega. But omega is frequency. There is no negative frequency. There is no negative time. That implies there is no negative frequency. So we'll only consider the positive value. So omega is equal to 4 becomes 2, and then k by m becomes under root k by m, and then sine square becomes mod of sine, because again omega cannot be negative. So this is the final equation, final form of our equation. So what is this equation telling us? We really see what are the so k is known. K is a spring constant. The stiffness, it's known. M is the mass. Mass is known. We're trying to A is the lattice constant. So the distance is known. Then essentially this is a relation between omega and q, where q is the wave number, right? Q is the wave number. So this is q. Q wave number, right? So essentially this is like omega versus q. So what is this plot like? It's easy to understand that this plot will never have uh, negative omega values, and we know that sine of any value, like it cannot exceed 1. So sine cannot exceed 1. So that means maximum value will be 2 under root k by m. That is the maximum value of omega that is possible in this system. And we see that multiple wave numbers are possible because sine can take any value of theta inside it, like phase inside it, but it is periodic. Uh, so it is periodic in wave number direction. That is one thing we notice. And we notice that there is the minimum omega is 0 and the maximum there is a cutoff. So this, so we can call that cutoff frequency simply. Omega cutoff is equal to 2 under root k by m. Now, what is meant by cutoff? What do you mean that omega above it is not possible? Of course, it's possible. Maybe like omega, maybe I excite it at an omega which is higher than this cutoff. And what is this cutoff? So essentially, what we are doing here is we are assuming some harmonic wave, and this is a sustained wave that is happening in this crystal. There's no external force. If there is slight um, if there's slight like initial wave, then that wave will sustain. That it's an infinite crystal, it will keep going. Uh, so these are like stable modes. Typically, if you have a cantilever beam or some structure, it has some fundamental modes. If there is motion in that fundamental mode, then it will continue in that mode. So so in finite systems, these modes are standing modes. But because this is an infinite system, there are no reflections there are no ends, so there are no end reflections. Uh, Hence, you can have stable propagating waves. So so that means that only waves in this frequency domain can propagate. And when they propagate, there is a certain wavelength which is indicated by the certain wave number in this system. So there is a certain wavelength and there is a certain wave number. So they can only propagate in this way. That means that this like You cannot have a stable wave in this region like for this frequency and this wave. No, that is not a sustainable wave. You can force it. You can, but we are not talking about forced waves. We are talking about free, uh, sustainable, stable waves. So yeah, that means that even here you cannot have a solution here. This is also not allowed. Then yeah, you can have a solution here somewhere. What is the other thing that that we notice? We notice that this entire this curve, this continuous curve, uh, we call this a band. So this is one band. And why did we get only one band? So the reason for that is we have 1 degree of freedom inside our unit cell, and because of that, you have 1 degree of freedom inside the unit cell. You you get a 1 degree of one pass band. So this is a pass band, right? These are the set of this describes the set of frequencies where your waves can pass. So yeah, just to highlight uh, important points. Now the question is, okay, so what we'll notice is that when when do we get omega is greater than omega cutoff? Right? If you try to see, let's say, okay, let's take a omega which is greater than omega cutoff. So let's take 4 under root k by m. So this is greater than 2 under root k by m. Right? This is greater than the cutoff. So what is happening? If you just try to find Then we get into this is in some range because we are neglecting the mod. So the sine inverse of 2, now that is going to be a complex number because typically for real values sine is not greater than 1. Sine inverse of 2 will be a complex number. That means that your q will be complex number. What is q being complex? Signified. So let's say q, the wave number, we can write it as alpha plus I beta. Let's say this is the real part, this is the imaginary part of the complex number. Then so if your harmonic solution is, let's say, in the form of e power I, then if you try to take this beta term out, you'll see that it becomes so there's a term here e power minus sorry beta x. That means that there is a decaying profile. Right, so this is one unit cell. So as you go forward, it's decaying. But yeah, so so the decaying profile is not sustainable, right? So that implies that if q is complex, if q is a complex number, then the profile decays. That means that wave cannot go from minus infinity to plus infinity. It's localized in some area. That's not a sustainable, stable, propagating wave. So similarly, like you know what happens when q is complex, then what happens So the answer that you can think about is just like how if wave number is complex, the imaginary part um, attenuates in space. Attenuation, I think it was covered in an earlier module. It attenuates in space. Similarly, omega is complex, then omega, the imaginary part of omega will make it attenuate in time. What is attenuation in time? Decreases in time. Amplitude decreases in time. Or there's another term for it. It's just dissipation. That's it. So if we are considering systems where there's no damping viscosity, then the omegas will not be complex. But if there is some damping, that's complex omegas, and that'll make systems dissipate in time. We'll just take a quick 5 minute break. Hi. So welcome back. Now the break is over. Come on, man. Where were you?
Hello? Huh?
Yeah, we were waiting for you.
Okay, hi, I had a call.
Okay.
Okay.
So yeah, this is what I have covered um, so far. Okay. So next,
Yes.
yeah, next I'll be showing. Let me attenuation. I think I was talking about attenuation. I think there was some plot you had earlier asked me about that plot. I think you liked that plot. I'll open that. Remember, there was some attenuation plot you were talking about. Hello.
Yes. There was some that attenuation plot which you showed earlier, or
Yeah, I haven't shown it in this course, but I think yeah, outside the course we had spoken
oh,
about it.
yeah.
So let me open that. Oh, where is that? Maybe. Yeah, found it. Yeah, can you see?
No, it's not shared.
No,
No,
it's not shared. Oh, why is it showing it is shared?
no.
Okay,
Maybe
let me,
maybe
okay, we
my
have
internet
shared.
is a bit slow because maybe Udbhav, you can
Now,
just wait. No,
now,
uh, no.
really,
Now,
nothing. Okay,
yeah. Now.
okay, awesome. So yeah, so if you have a look at you see on the plane you see real Q and imaginary Q. Typically, we only plot the real Q, and you see the blue lines. That is the dispersion curve that we typically plot, right?
Yes.
Yeah, but the thing is, there is also an imaginary Q, and if we plot the corresponding frequencies for both real and imaginary Q, we can get a plot something like this. So this is like a surface, like it creates a surface. I thought so since but however, what we typically concern ourselves with is okay. So now that you have seen this, let me and share it and go back. Yeah. So, so what we typically plot is we plot this portion, right? Let's say this is the cutoff frequency, and this is the real axis. This is the pass band, and beyond that is the pass band, right? And then beyond that we plot the yeah. This is the attenuation curve, and we call this the pass band. And the attenuation curve, it's actually along the imaginary q axis. So for the attenuation curve, we have imaginary part of q increasing. And for the real one, we have uh, real part of q this way. This is what we typically see. Although, like if we plot it fully, we see something like that. But this is actually enough for us. I hope that clarifies something. Yeah. So yeah. So what we see here. Okay. Are you seeing anything? Yeah. Okay. So we have talking about this band gap emerging out of this periodic lattice. So here's some work. So we can have a look at this work. This band gap, like this phononic band gap. So so this is the unit cell. In the corner, we see a unit cell in this figure. Um, so there is an aluminum-based cylindrical inclusion inside nickel. And then this unit cell is like periodic. And what they are showing here is that this is a band gap. So the shaded region is a band gap. So yeah, so it has been realized. This is the first paper that shows a band gap using periodicity in phononic crystals. And yeah, although this is a proper 2D lattice, but the concept is same and it's extended. So all we have studied it in 1D so far. And they say that this gap is attributed to Bragg scattering. So what is Bragg scattering? So try to understand Bragg scattering. So basically, I'm trying to show that Bragg scattering. There's a slide that I'm going to share. So Bragg scattering is so we see in X-ray diffraction that when X-rays are pointed at a crystal at certain angles, we see there's some condition that is satisfied, and when that condition is satisfied, we see really high reflectance. So right, so we see really high reflectance. That reflectance is associated with Bragg scattering. So so think about it like this. If yeah, I think I am missing the slide somewhere. So I'll just yeah, I'll just share. Yeah. So, so what? So we have some crystal, then we have X-ray, and then at certain angles we see high. So what is Bragg's condition? So Bragg's condition is, say if you have crystal, if the wavelength is lambda, let's say this is the lattice constant. If lambda equal to 2a, so this we're talking about Bragg's condition is 1D. Of course, if it's a 2D crystal, then angles are involved. There'll be some thetas, phi or something. But this is Bragg's condition in 1D. Right, so lambda is equal to 2a. What does that tell us? We know that q is equal to 2 pi by lambda. Let's find out at what q Bragg's condition takes place. So we know that q is equal to 2 pi by lambda. If you substitute in this here, then you get q is equal to 2 pi by 2a. That basically means q is equal to pi by a. So at q is equal to pi by a, we should observe Bragg's condition satisfied. That means at q is equal to pi by a, band gap should start. So do we observe something like that? That is exactly what we observe, in fact, that at q is equal to multiples of pi by a, we observe that the band gap starts from here onwards, right? And so that means that there is a certain periodicity that is associated with crystals, and that crystal and that periodicity causes Bragg scattering to take place. And Bragg scattering ensures that at q is equal to pi by a, there's a band gap that starts. And beyond that, we see that essentially the same pattern continues. So we just need to look at this this much area. What is that called? That is called this is called first relevant zone, and then you have the other ones that will be the second relevant zone and so forth. Uh, this is the first relevant zone, and in fact, this is enough to plot. This is enough to know the situation. Um, However, we see that waves propagating to the right and waves propagating to the left, they both behave the same way. That means that we can, it's a property of the system here, it's a simple system that you're taking. It's a reciprocal system. Whereas in non-reciprocal systems, you would have waves propagating in opposite directions, behaving differently. In reciprocal systems, this is enough to look at. So this is called irreducible relevant zone. Right, so this is sufficient to look at, and if you know this much, you can replicate the whole dispersion curve. Even if you have higher bands, this pattern follows. All right, so we move to the next next system that will analyze. So what is the next system that will analyze? We had 1 degree of freedom so far, right? So now that will take 2 degrees of freedom. So how do we take that? Maybe we can take two particles inside the unit cell, right? So maybe this is M1, this is M2. Maybe this is K1 and this is K2. This is K2. Why is this K2? Well, if this is not K2, then the degrees of freedom would increase because M2 has to connect to the M1 of next unit cell. So whichever strings connects the like M2 from right side has to connect M1 from left side. Right. So this is a dimer. That is equal to 2. This is a dimer. Right, and here also the motion is restricted to the horizontal axis. Now, what we observe, let's see what we observe. Before that, no, this is a general dimer. Why do we call this a general dimer? This will be very clear. But there are two more dimers, just subsets sort of. Uh, one is a stiffness dimer. One is mass dimer. Stiffness dimer. A stiffness dimer is basically yeah. So if you just look at mass, the masses are not varying. This is constant mass. So had you not known the stiffnesses, you would have thought it was a monomer. But once you look at stiffnesses, you see that there is an alternating pattern K1, K2, K1, K2, K1, K2. So that's a stiffness dimer because the stiffness is dimerized. The mass is monomerized in a way. Right? So similarly, what would be a mass dimer? Mass would be dimerized where you would have M1, M2, but stiffnesses would not be dimerized. So this is a mass dimer. Now, there are certain reasons why these are essential, which we'll find out later, but these are certain standard cases and they follow certain symmetry. So let's say these are mirror symmetric. The unit cell can be flipped and it would remain the same. And so whereas if you flip the general dimer, the M2 would come at M1. So that would not be inversion symmetric or mirror symmetric. Right? So there are certain consequences of such symmetries in bad structures. However, we'll not look at those things, but it's just important to know that there are two types of dimers, or rather three. Yeah, so now let's plot and see what happens when when we have a mass dimer. Let's take mass dimer. right? So M1, M2. So we can call this U1 of I, or we can call this U2 of I. Now remember that I refers to the unit cell, and both of these belong to the same unit cell, whereas 1 and 2 refer to these degrees of freedom inside the unit cell. So the first one talks about the degree of freedom inside the unit cell. The second one talks about the unit cell that we are uh, referring to. So in the same notation, if we follow, this will become U1 I plus 1. This will become U2 I minus 1. Right, so these are all the nearest neighbors that are going to affect each other directly. So since there are two masses, we can write the free body diagrams for each mass. So if we write for the first mass, it would be something like, say, M1 U1 I double dot is equal to, you can take K common here. I think there were two here, which we might be missing. Right, so this is the first mass. The second mass, we similarly will get Now we can combine these two equations. Yeah, before that, let's also think we need to write we'll notice is yeah, I think also we have to write 1 I plus 1, right? Using the block okay, periodic boundary. But here A would be its total distance. And what we'll get is we get K common. We get K common. Then um, okay, so this okay, so minus 2, minus 2, this will be 1 plus equal. So we can further combine this. We can write it in this form. We take this side, then we can write it like this. 2K um, wait for some. I think there is a minus sign here. Yeah, I think I forgot. There's a minus here because I need to write minus 1. Yes, similarly. Some small issue here, but yeah, I think overall it's not hampered. What is being conveyed? Okay. Okay, right. So now if we take, so how do we solve this? See, ultimately we want a relationship between omega and q, right? So that will give us the dispersion curve. So how do we solve? We take determinant on all sides, and then we'll see that if we take the determinant and on the RHS it's zero, so the determinant has to be zero of this entire term. But we know that like if u1 and u2 are zero, then that means there is no motion, and we are not talking about the kind of solutions that we see. So that would be a trivial answer. So what we need is a non-trivial answer. So for non-trivial answers, we need to ensure that this matrix is 2 by 2 matrix. The determinant of that is zero. So when you put that condition, the determinant of this matrix is zero. Essentially, happens is you get omega square into omega square. So it will be a quadratic. You just write it square and 1 2 plus k square plus this is zero. Try to break it down further. Take the first term and then the second term. e power x to e power minus x would be 1. So if you simplify this further, what you get is this can be simplified. There's an omega power 4 term, there's an omega square term. Then rest is a constant. So this is a quadratic omega square, and we'll only accept positive values. So this is c omega square is equal to minus of b. So what is b? B is this term. Minus or minus plus 2k into m1 plus m2. Whole divided by right. So, so what is this plus minus indicating here? It's telling us that there will be two frequencies for each q. So if we have a dispersion curve, so for each q we'll have two frequencies, and as q changes, these frequencies will change. So, right, so if we plot them, what should we observe? So, so we can take a hint. We can plot at q is equal to pi by k, and at q equal to 0. Why these two values? Essentially, due to the Bragg condition, q is equal to pi by a is where the band gap starts. So that and it repeats from there. And q is equal to 0 is also we've seen to be an important wave number beyond which you again get a mirror symmetric pattern. So these two values should be enough, at least for simple systems like these. Maybe we can touch upon what kind of systems uh, do not follow these laws, like whatever frequency cutoffs you will see at these two values, the entire, let's say you see some value like this. So this one value is another value that you'll find out. And you'll see that there's no maximum, minimum in between. Like this or this is not allowed. And that's because of the simplicity of the system. All the connections are direct. There's no long range connection. But why is that so? We'll not cover it in this module at least. What do I mean by long range connections? Let's say you have something like this. These are direct connections. These are all direct connections.
Shrikant,
Yeah,
I have a doubt. So I was curious. In long range interactions, do you see those type of curves that you've shown, like zero group velocity in the Brillouin zone? Like,
yeah. You see
okay, I
that,
didn't,
yeah.
I didn't know this. Like seriously. Okay, nice.
Okay. So you see something like this, something like this, something like this. You see,
Ah,
yeah, actually, let me just look for a paper. I think anyway, I was getting bored. I think it's a good idea to look for that paper.
yeah.
So this was a paper that Professor Rajesh had uh, given to one student named Krishna in presentation.
Okay.
Uh, how do I get that paper? Just give me 1 minute. Let me just look for that paper.
Yeah, sure.
Since when have you been actively listening about?
Yeah, I would say. I think I would say full 2 hours.
Really?
Hmm.
Oh, I thought you'll have a look at the recorded lectures.
No,
That's
no.
what students
Hey,
typically
I'm new to
do.
this field. I'm new to this
Okay,
field, so yeah, I don't have much idea.
okay, that's encouraging. Like any student showing this much interest, like I think
Yeah, yeah.
ISSS
Thank,
course.
thank you.
Yeah.
No, but
So,
genuinely, yeah, this paper, bro, like this is, yeah, something interesting. I think I might have overlooked this fact.
yeah, I'm looking for this wave propagation. So he uploaded one Excel sheet, and in that Excel sheet, I think he view assignment. I think it's an assignment. So let's say you heard of lateral local resonance, right? The truss-based systems.
Yeah.
Yeah, interestingly, even they are not long-range interactions. Although it seems like there's an intermediate uh, particle, but they are not, yeah, founded. Yeah, so long-range interactions would be something like, or even beyond, like something like this.
Hmm.
It's a beautiful paper. Yeah. Share this window. Where is it? Share this window. Share.
Yeah.
Can you see?
Wait, wait.
Can you see something
Nothing.
apart from nothing? Okay, I think I'll share. Share this window. Share. Share. Sharing.
Now I can see.
Right. So you look at this unit cell. Let's say this is a monomer typically,
Uh-huh.
but you see that by K2 they mean that it's connecting to the second furthest neighbor, and by K3 they mean the third. K1 is the direct one, and K10 means the 10th. That is what they are saying. But if you really think about it, this is just a monomer because
Hmm.
every particle is connected to, let's say, till the 10th nearest neighbor that it has. Right. So this is what you observe. Can you zoom? Can you see this?
I think you can download the paper. Right? It will be better, right? Uh, yeah.
Can you see it?
Yes. Okay.
Uh, yeah. So this is the Brillouin zone. So it's like it's normalized QA by pi, right? So this is the end of the Brillouin zone,
So unit
and
cell
yeah,
for a long range interaction, it won't change, right? I mean, it would be.
it will be a
Um,
monomer. Unit cell will
yeah.
not change because every particle is connected to its, second, third, fourth neighbor, whatever.
Okay. Okay.
So it's still
Both
a
sides.
monomer that
Uh-huh.
both sides, all particles, both sides. So so that is why, right?
Okay. 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 Yeah. Yeah. Got it. Got it.
If
Understood.
particle number I is connected to I
I
plus
plus
2,
two. Yeah. Yeah.
then I
Yeah.
plus
And I
2
plus two.
also is connected to I, right?
I.
So
Okay. Okay. Okay.
yeah, so these are the various connections that they have found, like they're tuning like the number of connections and the intensity of them, and they can totally get maximas and minimas within the brilliance zone. So
Like I think I only recalled about that inflection point, like that D curve. Okay, I didn't know key. Seriously, I didn't know whether like we have both maxima minima. So okay, that's something I think we can look into it. This is
yeah, definitely. So this is actually the basis for a lot of analytics, even in fields like topological systems and stuff, where it's important to know the maximum minimum values, and then from there you can, if you want something like band gap to, um, disappear, then you want two bands to sort of maybe touch, then
yeah,
in a right? So then analytically, if you want to get certain expressions, then you have to use this as the basis. Although, uh,
hmm
so this is what it's showing, that in long range you can get this, but um, in monomers and I think in simple systems you can still prove that that if you do not have long range interactions, then the maxima and the minima happen at the end of the Brillouin zone. But I think there's still no generalized proof that
yeah,
for any system that you consider, it will be like that. So so the analytics like are may not be
yeah,
like uh, like you have to verify the analytics if they are true. So you cannot be conclusive in such cases,
yeah.
and because there is no paper, and this is also something something
Recent
like
paper, right? Yeah.
this is a recent paper. I haven't seen. Yeah, it's fairly recent.
Oh, yeah.
Yeah.
Like, because what I was wondering, if you have both maxima minima in your like dispersion curve, so it means ki for one frequency you have then two wave numbers. Like,
Yeah.
oh, that's I should look more into this system. I think we both can figure something out of it.
Yeah. Sure. I think it would be it would be even interesting to maybe see what happens when let's say two bands
Hmm.
touch not at the end of the brilliant zone
Yeah,
but
but
in the
in
middle.
between, yes.
So
Hmm.
yeah, would you get some interesting this thing? And what happens to? I think yeah, this is
Have you tried long range interaction? Like, in
yeah. I've tried in some systems. I've tried in these lateral local resonance. Those type of systems I've tried. And you get similar results, like not
Mhm.
exact, but it basically yeah, you get some beautiful patterns. I'll share it later. I'll have to find where exactly those results are. But yeah, the but you get similar trends that you get some local maximas and minimas. Um, I think our primary objective was something else, and we're trying that.
Mhm.
But
Nee, okay, okay, got it, got it.
yeah,
Yeah,
and then
because I remember from yeah that presentation that okay, yeah, no, this is something okay. I'll look into this. I think yeah we so I was just wondering like can strain theory be applicable to this long range interaction also deformation theory basically. Um,
information.
yeah, yeah.
Okay. And how do you think that would particularly help?
So sort of revealing topology in deformation sorry revealing hidden topology in these long range monomer chains or even long range 1D systems. I think
Mhm.
yeah, yeah. So um yeah, it's something which I feel could be done
The
because
strains could be taken in a different way, I think, right? Like, so, I think you're referring to that.
spring elongations, yeah,
Yeah. Okay.
yeah, in a chain, yeah.
Hmm. Yeah, interesting. I think so. Definitely interesting. I would maybe uh, look at also at some sort of a long range dimer, some really simple
Yes.
long range dimer, and if you could show that this is how the bands touch and what is the effect of it? Does that change the topological nature, which will be covered at the end in the advanced topics? Does that change that? So, but yeah, for now, I think we can say that band touching is important. So this is one of the things I was gonna do in timers. I was gonna show. I think I'll show now what
Oh,
band
okay, okay.
touching
Yeah, yeah.
is,
Continue.
but of course not in like the topological nature of these timers will not be discussed at this moment because that would be a deviation too soon.
Yeah, yeah.
Yeah. So so yeah. Okay, let me. Uh, I think I'll end the lecture in some time. Then we can think catch up more on this.
Oh, no, sure, sure, sure. We can continue. Yeah.
Uh, where was I? Yeah, so fundamentally, like if you do not have these long range interactions, then you can say that you can just check at these values. Q is equal to pi by a, Q is equal to 0. So what do we get? So we get that so 1 omega starts from here for the we know there will be two bands because it's a 2 degree of freedom system, and we covered like that number of degrees of freedom is reflected in number of solutions to omega and hence the number of bands. So we know that there will be a band from 0, and we will later cover cases where bands are not from 0. Um, then there has to be some sort of a grounding potential there. So this, and then we'll see that it takes the shape of something like this. Now, what are these values going to be? And this is the band gap region, right? And this is the cutoff region. So in the monomer case, we saw that there is something called a cutoff above which there are no stable propagating solutions. Whereas here, for the first time, we are seeing something in between the pass bands. So we can call this band gap. Now, could you call the cutoff as band gap? Actually, you could. You could call that also a band gap. But typically, when people say we're talking about band gaps, they're talking about gaps between pass bands. So, so this is very fundamental to metamaterial study. So, okay, what is this? These values, like it depends on it is 2k by m. Let's say m1 is greater than m2, right? If that is the case, then we'll notice that this will be m2 and this will be 2k by m1. This is just by solving this equation. Then, right, so this will be 2k m1 plus m2 whole divided by m1 m2. Right, so this is the cutoff frequency and this is 0. Okay, so one interesting thing, I think what Ubha was also talking about was band touching. So what do you mean by band touching? If we uh, assume that M1 and M2 approach each other, what will happen is mathematically you'll see that uh, these values approach each other. Right? So this comes down, this goes up. And at some point when M1, right, so when M1 is equal to M2, these two values, they're the same. So the band gap has closed. Right? So what is that case? That is nothing but a monomer because M1 is equal to M2 is equal to some M. That's a monomer. Right? And what is this value then? So this value is 2k by M. Right? So what is this value then? If you substitute M1 is equal to M2, you'll get it is 2k 2M by M square. So this is nothing but 2 root k by M. This is the same cutoff frequency that we observed in the monomer case because this is the monomer chain. But there's only one anomaly here, that there are two bands. Why is this happening? Like Q is equal to pi by A, right? So what is this anomaly? This is this anomaly is existing because the definition of A has changed. earlier when there was a monomer, right? So we're calling this distance A. So this is monomer. Now that we have a dimer, and this was, let's say, M1, and then this was M1, but this was M2, we're calling this as A, right? So, but this is a dimer, and in the case when M1 is equal to M2, everything is same, but the definition of A has changed. So what has that led to? So the value of A here is is quite high, not quite high. Okay, so I think in this case double. So that means if it weren't double, then the monomer should, for the monomer case, this is the brilliant zone. This is for the dimer case. For the monomer case, this is for the dimer case. That means the band should have been something like this. But instead, because of us wrongly choosing 2 times A, the band has folded. So this is called band folding. That means we have not chosen A appropriately. Or maybe it's a higher degree of freedom system like some dimer, but because of some parameters matching something, it's become a lower degree of freedom system, like a monomer. So something like that is happening. So when band closes, exactly at that transition point, like we see band fold. Anyway, it's a critical case. So yeah, so this is the content so far. Yeah, and another thing is this lower band we call it acoustic, and this higher band we call it optical. Is there a yeah? We'll cover this further, um, and we'll see how these modes look like. And then later we'll go into locally resonant systems and grounding, lateral local resonance, inertial amplification. So there's a lot to come in the following module. So yeah, thank you for joining. I think that is the end of this class. Yeah, UV, you're still there?